Okay, I think we can start, right?
We can start now.
Okay. I welcome everyone warmly to this session, Data-Driven Modeling for Cooler Cities, as part of the conference Innovate for Cities that UN Habitat and GCOM is leading. The conference brings together science, innovation, policy, and practice to support cities to take climate action. And we all know that urban data is very crucial for analyzing the climate situations on site and proposing good solutions for reducing the emissions. I'm introducing myself. My name is Geza Zima. I am academic lead of UNITAC. It's an innovation accelerator of cities based in Hamburg. It's a UN Habitat entity, a cooperation with Hafen City University and OICT. And our research and action focus is to develop and implement urban data tools and also frontier technology for cities and regions to address their challenges. We mainly focus on informal settlements, and we are experts in setting up citizen engagement tools, planning, support systems, and also data management platforms. So I am the moderator of the session, but I'm in a kind of double function. I'm also a researcher, and I'm very interested in all the tools that you are going to show us now. And of course, climate is also very important in our research area. Yeah, the focus here on this panel is the question of how we could overcome the heat island effects in cities. And we have three very interesting speakers here today. I will introduce them briefly, but Pedro is already there. Pedro Montesinos, he will give an input, a lecture with Alberto Di Thomas about Buenos Aires. It's a showcase that we are going to see. Then there is Parisa Kloss. She is the head of the Resilient Urban Planning and Development. It's a company that is based in Germany, and their expertise is integrating climate data to urban planning. I'm very happy also to see you here, Parisa. And then we have another guest here on this podium, and this is Maria Bella Sosa. She is not here in person. She pre-recorded her video, and she will give us an insight of a case study in Mendoza, Argentina. Yes. Some notes about this issue of heat island effects in cities, because I think it's a big issue all over the world. On different continents, we of course have different challenges. The reasons why this phenomenon takes place is different, but nevertheless, I think it takes place all over at the moment, because cities becoming bigger, many parts of cities become denser. We often use construction materials like concrete and steel that heats up quarters of cities. We have addressed new forms of mobility. Topography, land use, vegetation plays a major role. And there are many factors that cause to heat up cities. We have to build mixed areas with green areas, open spaces, reduce private cars from city centers. We think about green rooftops in Europe a lot, and also green facades. Let's call it a green infrastructure, and how we can put this to the city when the city becomes bigger and more denser. And we know that this whole topic is closely connected with air quality, also with health issues, and then also with social justice. I think this is also very important. It's not only an issue about climate, let's put it in a very rational, objective way. It has also a lot to do with the social question of how we can set up social justice in cities and regions. And there are many different actions and steps that cities are taking to create impact at the moment. And we know, and this is very interesting for me also as a researcher, that heat effects are not so easy to measure, because it's dynamic data that we are dealing with. So it varies at different times of the day. Weather plays a major role, and also seasons, and also day and night. So it's not so easy. We have a lot of data in the city that is much more easy to measure. When we speak about spatial data, for example, it's kind of static, but air data are also climate data is very complex to collect and also to modelize. Okay, I'm very delighted to introduce the speakers now, and we will start with Maria Belen Sosa. She is an architect at the Instituto de Ambiente y Habitat y Energía. And she gives us an input, a presentation with the title Microclimate Assessment of Different Urban Patterns, Densities and Buildings, Footprints, Shapes. It's a case study from Mendoza, Argentina. And I will try to share my screen now and show you her pre-recorded video. She's not here, like I said, but we can nevertheless refer to her input in our discussion afterwards.
Hi everyone, my name is Maria Belén Sosa, and I am going to present our research entitled Microclimate Assessment of Different Urban Patterns, Densities, and Buildings Footprint Shapes, Mendoza, Argentina, as a study case. Okay, in the recent years, low-density areas of cities have been densified. This urban planning intervention is needed for achieving sustainable compactness development. But the way this development impacts on the boundaries microclimate condition is not always a sustainable pathway. This study assesses the air temperature modification in the summer season for Mendoza, an arid city located in the western of Argentina that have been intensified the urban density in the last year. Particularly, we have a period that the urban advance added 2,000 hectares in only 4 years. In order to quantify this impact, a series of mixed density urban scenarios at neighborhood scale were tested. We combined 3 urban patterns, 7 building footprint shapes, and 2 densities. Urban patterns, we use rational, cul-de-sac, and organic. For building footprint shape, we so-called box, ribbon, rotating ribbon, cone, rotated cone, U-shape, rotated U-shape. And we use the low and the medium density, taking into account 3 meters for low density and 9 meters for medium density. The methodological process of this research takes previously development low density scenario. Here in the figure, you can see the 3 urban patterns, the rational, the cul-de-sac, and the organic. These first 3 images are the so-called base cases. There are low density cases with 3-meter high houses. These scenarios, we called it base cases. Then we made this densification process, generating the mixed density neighborhood. We take the central 4 blocks of each urban pattern to densify. Here you can see all these urban scenarios. We have a result that we can combine these 3 different shapes, and we have 21 mixed density neighborhoods scenarios. So you can see here these layouts. Also, here in this image, you can see the figures assigned to each of the building's footprint shapes, and a cake chart that show us that we have maintained homogeneous the percentages of the building footprint shapes in each layout, in each scenario. They take the 10% of the total area. Then the difference in the assigned areas are related to the open park space, being the cul-de-sac pattern twice than the rational and the organic pattern, 24% versus 12%. This figure shows us the location of the receptors. The receptors are the points that ENVIMAT software uses to collect data. There are the sensors in the outside of the scenario. These receptors are distributed in each layout and then aggregated for the analytical process. So we have 3 that takes the microclimate condition of the urban canyon, 4 of the boundaries, and one inside each open public space. The simulation area has 250 meters. This chart, this figure, shows us all these behaviors of each of the scenarios and aggruppated for urban pattern, but differences by the scale of analysis. The 3 UC receptor, 1 the OPS, the open public space, and 4 of the boundaries referenced with the B in the chart. In the first column, we can see the base cases thermal behaviors, maximum, minimum, and average air temperature in Celsius degrees. This figure shows us that by comparing the base cases with the mixed densities ones, we can see that cul-de-sac pattern is the warmest at the 3 scale of analysis, at the urban canyon, at the open public space, at the boundary conditions. This pattern needs to incorporate shade in the central open space by a proper landscape design adapted to arid regions. The rational urban pattern is the coldest, is the best at thermal point of view. The cone and rotated ribbon are the best building footprint shapes, and increase the density. Here we can see that it's not so harmful in terms of outdoor thermal behavior by a proper combination of pattern and building shape. So rational pattern, as you see scale, the rotated ribbon building footprint shape has the best thermal behavior. Being this the scenario colder at the mixed density than the base case. Cul-de-sac pattern at the UC scale, all the building footprint shapes are warmer than the base case. For the organic pattern at UC scale, cone building footprint shape has the best maximum and average thermal behaviors, and the rotated ribbon keeps the same minimum air temperature than the base case. At the UPA scale, the rational pattern have the best thermal behaviors. The cone building footprint shape achieve the lowest maximum and average temperatures, and the rotating ribbon keeps the lowest minimum air temperature. At B scale, the boundaries, the rational pattern, rotating ribbon, building footprint shape have the best thermal behavior. This is the first step study that indicates that when the mixed density areas are included in the low density neighborhood, the thermal impact is reflected by the urban pattern layout. So in this sense, we can say that the urban form of a neighborhood is a vital variable that can reflect the thermal behavior in the planning stage. The challenge we face now is what is the best combination of mixed density inside low density areas, and in which extent can improve the outdoor thermal comfort and microclimatic livability of a community by incorporating mixed densities. Thank you so much for your attention. I leave you here my email contact. I represent INAE of the CONICET institution in Argentina. Thank you so much.
Thank you, Maria, for this presentation. And I saw that you just joined the conference. Is this right? Are you in the call now? I see you at least on my screen. Welcome, Maria. Hello. I introduced you to the panel. I introduced a little bit the issue of this panel, and it's good to see you. Will you be there for the discussion afterwards? I hope so. If yes, then we would go for the next one. Then we can discuss it all together afterwards. So then I would hand over to, she has a problem with her microphone and her camera. So that means that you cannot talk to us, probably. Maybe you can fix the problem while Pedro is speaking. If not, then you can listen and write into the chat, and then we take your questions or comments from the chat. That will be possible too. Okay, so thank you very much for this. Our next speaker will be Pedro Muradas Montesinos and Alberto Di Tomas. Pedro is here, Alberto is not here. They are both vulnerability and climate risk experts at IDEM. IDEM is a company that is based in Madrid. and they will give us an input about urban parametrization and local climate zones definition in the meteorological simulation of the urban heat island effect. The case study that we are going to see now is Buenos Aires. And I welcome you, Pedro, and yeah, the floor is yours.
Thank you, Gesa. Thank you, the organization, UNED Habitat and the Covenant of Mayors for having us here. It's a pleasure for me and my company Dom being here. And I will share my presentation. It's a pre-recorded presentation as well. We remain in Argentina as well. So we could add subtitles to the presentation, but we count with professional interpreters on board. So I will be able to ask you further questions after my presentation. Let's go. I will share my screen.
Muy buenos días, buenas tardes, buenas noches para todas y para todos. Mi nombre es Pedro Muradás y junto a mi colega en IDOM, Alberto de Tomás, vamos a presentar nuestro trabajo de caracterización de la isla de calor urbana atmosférica en la ciudad autónoma de Buenos Aires. Esperamos que la contribución sea de su interés. Nuestro principal propósito en el contexto de este evento es poner a disposición y compartir una serie de conocimientos adquiridos en materia de gestión de este fenómeno de isla de calor urbana. Se trata, pensamos, de insumos técnicos pues, que son de gran valor a la hora de planificar y gestionar las dinámicas urbanas en nuestra ciudad. Simplemente para alinear un par de conceptos, yo creo que en este foro pues casi todos tenemos pues un conocimiento más o menos preciso de ese efecto isla de calor urbana, que es la diferencia de temperatura que se registra entre nuestro entramado urbano generado pues por el crecimiento, la expansión de nuestra actividad cotidiana en las ciudades en relación con el entorno natural que le rodea. Ese efecto, lógicamente, es un efecto completamente artificial generado pues por la actividad urbanizadora y ese diferencial de temperatura pues genera esa isla de calor urbana. Lo que nos interesa en este momento compartir con ustedes es la idea de que no se trata de un concepto lineal en el espacio-tiempo, sino que dentro de nuestra propia ciudad pues hay áreas en las que esa isla de calor se manifiesta de forma más patente y además es variable tanto a lo largo de un día como a lo largo de un año. Presenta diferentes variaciones y esa amplitud, ese diferencial térmico, es diferente dependiendo de cuándo lo estemos registrando. También es interesante en términos de análisis, de aproximación técnica, de caracterización, distinguir dos tipos de isla de calor urbana. La superficial, que sería la que nos reporta, la que nos dan la temperatura que nos devuelven físicamente las superficies que vamos encontrando a lo largo del entramado urbano, edificios, pavimentos de la red viaria, pero también las áreas verdes urbanas, ¿no? Se mide esa temperatura y esa temperatura es el indicador que nos caracteriza la isla de calor superficial. Y por otro lado tenemos la isla de calor atmosférica, que se mide, se reporta con la temperatura del aire, generalmente a 2 metros, a una distancia del suelo, y se corresponde pues, con la temperatura que nosotros percibimos y experimentamos en la ciudad. Nosotros hemos trabajado caracterizando en este caso concreto la isla de calor atmosférica por medio de modelos de simulación que nos permiten tener un dato de temperatura para toda la extensión de nuestra área urbana y alrededores y poder comparar. También mencionar en este contexto que la isla de calor urbana tiene una clara vinculación, aunque no es un efecto climático per se, pero sí que acentúa, hace más graves los posibles efectos que variaciones en los máximos de temperatura podamos llegar a experimentar en las próximas décadas en nuestras ciudades, como parece que así va a ser. En términos de adaptación, actuar para mitigar nuestra isla de calor urbana es una medida de adaptación que nos va a permitir ser menos vulnerables y mejorar nuestra capacidad adaptativa, ¿no? Por tanto, no sufrir los potenciales efectos sobre la salud derivadas de las temperaturas extremas en nuestra ciudad. Pero también es interesante señalar que actuando sobre la isla de calor urbana también conseguimos indirectamente atender el eje de mitigación, porque probablemente logremos en esas épocas de calor extremo llegar a reducir nuestras necesidades en consumo, por ejemplo, de aire acondicionado, ese consumo eléctrico, y estaremos por lo tanto reduciendo las emisiones necesarias, ¿no? para mantener la temperatura en términos tolerables, ¿no? y agradables para nuestro bienestar. Sin más, pasamos a hablar de nuestro trabajo que hemos completado. Se trata de un análisis, una contribución técnica hecha en colaboración como parte de la iniciativa de C40, la red de grandes ciudades internacional de liderazgo climático, que ha prestado apoyo técnico a la ciudad de Buenos Aires para completar su plan de acción climática. El proceso de elaboración de ese plan de acción climática ha sido muy rico en términos de análisis, de participación, y ha permitido ir produciendo insumos de gran interés para que las medidas que ese plan de acción climática contiene pues sean lo más sensatas, lo más factibles posibles. Como parte de ese esfuerzo colectivo, desde IDOM hemos contribuido realizando diferentes análisis técnicos, hemos hecho análisis de riesgos climáticos, hemos definido diferentes medidas de adaptación al cambio climático y también hemos hecho algún estudio complementario como esta evaluación estratégica para reducir el efecto de isla de calor urbana en la ciudad.
Para introducir el contexto urbano en el que hemos trabajado, es la Ciudad Autónoma de Buenos Aires. Comentar brevemente que la ciudad tiene una población de aproximadamente 3 millones de habitantes en una superficie de 200 kilómetros cuadrados. Esto hace un territorio densamente urbanizado, prácticamente en su totalidad, con presencia regular de áreas verdes y espacios abiertos. La Ciudad Autónoma de Buenos Aires, asimismo, se engloba dentro del área metropolitana de Buenos Aires, que es una superficie mixta de espacios urbanos y cultivos que alberga aproximadamente 15 millones de habitantes. Para el trabajo realizado hemos utilizado el modelo meteorológico WRF, por sus siglas en inglés Weather Research and Forecasting. Es un modelo de mesoescala diseñado para describir o predecir las condiciones meteorológicas, desarrollado por varios institutos estadounidenses y que modeliza los flujos verticales de energía con objeto de resolver fenómenos que tienen lugar en la capa límite planetaria, que es fundamental para entender la relación entre el contexto urbano y la atmósfera. Este modelo hace uso de factores como topografía, usos del suelo, tipos de vegetación, clases, fracción vegetativa, índice de área polar o albedo, y ha sido implementado en esta consultoría por la Universidad Politécnica de Madrid, bajo sus procesadores computacionales, utilizando la parametrización BEP, que por sus siglas en inglés significa Building Effect Parameterization, que tiene en cuenta el impacto que los edificios tienen sobre el flujo del aire. Es un modelo dosel multicapa que representa la interacción directa de los edificios con la atmósfera a través de propiedades geométricas, térmicas, aerodinámicas de los diferentes usos del suelo urbano. Para la simulación de este caso de estudio hemos implementado dos periodos de tiempo, uno correspondiente al periodo de altas temperaturas o estival, que en la Ciudad Autónoma de Buenos Aires se corresponde con los meses de enero y febrero, y a su vez enero-febrero de 2020, que corresponde con un periodo de temperaturas extremadamente elevadas en la ciudad. Asimismo, se simuló un periodo invernal correspondiente a julio del mismo año, 2020. Hemos simulado un caso base con las condiciones estándar de comportamiento térmico de la ciudad, así como diferentes escenarios con medidas de adaptación para ver la atenuación del efecto isla de calor a través de las simulaciones, como veremos más adelante. La resolución espacial de trabajo del modelo es de 1 kilómetro cuadrado, para el que se han categorizado los diferentes usos del suelo, como veremos en la siguiente diapositiva, y se trata de un modelo meteorológico que utiliza diferentes dominios anidados, como se ve en la figura de la izquierda, de 3 por 3 kilómetros, 9 por 9 y 27 por 27, para dar las condiciones de contorno para inicializar el modelo. En la metodología de trabajo hemos implementado la caracterización de zonas climáticas locales desarrollada por Stewart and Oak en estudios previos y mundialmente conocida, en la que se caracterizan los diferentes entramados urbanos en zonas homogéneas, atendiendo a regiones de la cubierta urbana uniformes en términos de superficie, estructura, materiales constructivos o actividades humanas. La Ciudad Autónoma de Buenos Aires encontramos 5 categorías diferentes, atendiendo al propio entramado urbano, el ancho de las calles, la altura de los edificios, las materiales constructivos. Así podemos encontrar el centro urbano o microcentro, llamado en la Ciudad Autónoma de Buenos Aires, con avenidas con edificios comerciales de más de 6 alturas y arbolado urbano disperso. También encontramos un uso residencial con espacios residenciales de entre 3 y 6 metros de altura, con presencia patente de arbolado, un uso residencial abierto, con viviendas de 1 a 3 alturas y arbolado más denso. Es la zona climática que más abunda en la Ciudad Autónoma de Buenos Aires. Encontramos también diferentes villas y asentamientos que son viviendas informales de baja altura y con prácticamente ausencia de vegetación, así como determinadas y muy concretas zonas industriales y logísticas con materiales más metálicos correspondientes a naves industriales y a centros de distribución logística. En la siguiente simulación, resultado del modelo WRF, podemos observar la variación de la temperatura a 2 metros, que ha sido la variable de análisis para analizar el efecto isla de calor en la ciudad de Buenos Aires para el periodo estival de febrero de 2020, correspondiente a altas temperaturas. Podemos ver la evolución dinámica de la variable a lo largo del entramado urbano en las diferentes horas del día, y nos puede ayudar a entender el comportamiento térmico de la ciudad para proponer soluciones encaminadas a mejorar el confort térmico. En los resultados obtenidos del escenario base para la parametrización de la ciudad, encontramos en las figuras de la izquierda el escenario estival, los valores promedios correspondientes al día o al periodo nocturno, así como la media diaria y a la hora de máxima temperatura correspondiente con la máxima elevación solar. Y atendiendo a esa última figura de la máxima elevación solar o máxima temperatura, podemos observar cómo el microcentro de la ciudad autónoma es el que alberga mayores temperaturas en comparación con los barrios subyacentes, ¿no? Podemos ver cómo esa diferencia de temperatura alberga hasta 4 grados de diferencia, de 30 a 34 grados de diferencia, en relación a los barrios que se encuentran en la zona costera del Río de la Plata, por la influencia térmica que el propio río proporciona a la ciudad, así como el río Riachuelo, que se encuentra al sur-sureste de la ciudad y que reduce también ese efecto de isla de calor en los barrios circundantes. Para las condiciones invernales, en julio del 2020, podemos observar prácticamente el mismo comportamiento de la temperatura a 2 metros en la ciudad, si bien esas diferencias del microcentro con el resto de barrios circundantes son en torno a 2 o 3 grados, es decir, ligeramente inferiores a las condiciones estivales debido a la propia situación invernal, así como al efecto de las altas temperaturas dadas en el periodo analizado para el periodo estival.
Una vez caracterizada espacial y temporalmente la isla de calor urbana en la ciudad, el siguiente trabajo que completamos fue definir junto con el equipo técnico municipal de la ciudad qué medidas, dónde incluirlas y con qué prioridad, ¿no? Para poder atenuar ese efecto. Básicamente nos centramos en tres grupos, tres tipologías de medidas de atenuación de la isla de calor urbana, centrándonos en primer lugar en la infraestructura verde, tanto en el incremento del arbolado urbano, pues la ciudad tiene previsto plantar en los próximos años varios decenas de miles de nuevos pies de arbolado y les hemos ayudado a priorizar y a localizar las áreas más adecuadas para situar esos nuevos pies de arbolados. También áreas verdes de recualificación, porque en algunos casos el área, la superficie está dotada, pero es necesario mejorar sus características en términos cualitativos, de vigor vegetal, de frecuencia de riego, de replantación. Y también hemos trabajado con techos verdes y fachadas verdes en determinados puntos de la ciudad. Se trata de un complemento a la infraestructura verde que, bueno, pues tiene que ser analizado con cierto detalle dónde puede ser implantado o no, pero también hemos trabajado con este tipo de soluciones. Moviéndonos a los elementos fríos, a los cool roofs o cool pavements, que se denominan en inglés, hemos también propuesto en algunas áreas actuar directamente por medio de superficies y de materiales que lo que hacen es mejorar las condiciones e incrementan el albedo de tal forma que evitan que las superficies acumulen calor. Hemos de decir que en términos de costo-eficacia, estos elementos fríos o frescos son los que realmente pues actúan de una manera más eficaz, hablando exclusivamente de la reducción de ese fenómeno de isla de calor urbana. Finalmente, también hemos planteado, en conjunto con la infraestructura verde, en algunas áreas de la ciudad especialmente proclives para ello, la mejora y la creación de nuevos elementos vinculados al uso del agua, la infraestructura azul, que en combinación con la infraestructura verde pues generarían, ¿no? esos corredores, ese entramado urbano que a efectos regionales pues puede inducir una reducción de ese fenómeno de isla de calor. Hemos trabajado dentro de nuestro último dominio anidado de 1 kilómetro cuadrado, viendo celda a celda, píxel a píxel en nuestra retícula de trabajo, las áreas que eran más adecuadas para colocar cada una de estas medidas planteadas por la ciudad. Los resultados obtenidos son los que estamos mostrando en este slide, que se trata de una resta espacial de escenarios. Lo que hemos hecho ha sido restar la temperatura que los escenarios, las medidas están generando respecto al escenario base. Entonces, ustedes ven que estos tonos más azules lo que están reportando es la reducción de la temperatura que están generando esas medidas que hemos planteado en diferentes áreas de la ciudad. Como ven, el margen de eficacia que estamos reportando llega incluso hasta el 1,5 grado centígrado, grado Celsius. Eso es, pues, en términos comparativos y en relación a estudios anteriores que hemos realizado, bibliografía, pues es un margen de maniobra bastante aceptable y que no hace más que avalar y respaldar la idoneidad de promover este tipo de medidas de infraestructura verde en nuestra ciudad. Simplemente terminando con una serie de ideas que queremos compartir con ustedes para finalizar esta exposición. Tenemos que tener claro que para caracterizar adecuadamente la isla de calor urbana, tratándose de un efecto regional, necesitamos instrumentos que trabajen y que sean capaces de darnos información de mesoescala que permitan comparar nuestra área urbana con nuestro entorno rural y también dentro de la propia ciudad identificar qué áreas son hotspot en términos de temperatura y esas islas de calor dentro del propio entramado urbano. Necesitamos tener estudios que sean bastante ambiciosos en ese sentido. Nosotros hemos podido trabajar únicamente con 2 periodos de 10 días en la modelización, no teníamos más tiempo para eso, pero creo que es prudente recomendar al menos trabajar con estaciones, un año completo, para poder entender cómo se comporta realmente a lo largo de un ciclo anual ese fenómeno térmico, ¿no? en nuestro clima urbano. Las soluciones igualmente no pueden ser puntuales. Tratándose de un efecto regional, tenemos que actuar de forma ambiciosa. Tenemos que tratar, inducir, generar áreas verdes con una superficie mínima y que estén interconectadas entre sí para poder generar y atenuar ese efecto que es regional, insisto. También es importante señalar y que las medidas que estamos promoviendo son medidas de no arrepentimiento, en el sentido de que no solo impactan positivamente, como estamos demostrando, para reducir la temperatura de la ciudad, sino que además generan otra serie de beneficios en términos de reducción de la calidad del aire, mejoran la salud, la inclusión social. En términos ambientales son medidas también beneficiosas. Por último, queremos señalar que este tipo de aproximación, trabajar con modelos meteorológicos de mesoscala en nuestras áreas urbanas, metropolitanas, admite y llama realmente a modularse, a concatenarse con análisis de calidad del aire. Generalmente se trabaja con modelos meteorológicos como el que hemos implementado en este caso, acoplados a modelos de gestión de la calidad del aire. Y ahí estaríamos proporcionando a nuestros tomadores de decisiones en nuestra ciudad de buenas herramientas para hacer una buena gestión ambiental en nuestra ciudad. Y bueno, ya estamos en tiempo. Simplemente agradecerles su atención en este espacio que nos han concedido, agradecer a la organización del evento la oportunidad, y estamos a disposición. Aquí tienen nuestros datos de contacto, y un saludo para todas y para todos, y que tengan una feliz jornada.
Saludo.
Yeah, thank you so much, Pedro, and also greetings to Alberto for this presentation and for this differentiated insights of your research or your tools. So we have seen 2 very hyperlocal solutions for heat effects, one in Mendoza and one in Brazil. And I have already a lot of questions, but before I start to ask my questions, I would like to introduce our next speaker, which is Parisa Kloss. Happy to see you, Parisa, and very happy that you are part of this panel here. You are the executive director at Resilient Urban Planning and Development, a company that is based in Germany. And yeah, your presentation is a live presentation, and we are very, I don't know if you're sharing the screen too. I think so, yes. Maybe. Yeah. Okay. So I hand over to you. The microphone is yours. Thank you.
Thank you. Yes, thank you so much, Gesa. And hello, everyone. Thank you so much. First of all, thank you so much for inviting me for this session. Actually, before losing time, or in order to save time, I would immediately like to dive into my presentation. My presentation has 2 parts. In the first part, I would like to share with you a simulation-based approach to identify the hotspots in multi-dimension and developing scenarios, prioritizing them, and to reduce the actual risk in those areas and plan for the action. And in the second part of my presentation, I would like to somehow open a dialogue to discuss further how the introduced approach can bridge the potential gaps. Before actually starting the main part of my presentation, I just wanted to briefly mentioning the challenge. We know that actually urban development contributes to economic growth. We also know that developing without paying attention to local climate and extreme weather also causes lots of critical and long-term effect on the environment. For example, incorrectly located, oriented, and also designed multi-story buildings and high-rises can create microclimate changes that we are calling it actually urban heat island phenomena. So how we can solve this problem and have resilient urban development that can help us to achieve resilient economic growth and at the same time resilient urban climate change planning. So actually, in order to take the best action towards actually tackling urban heat island effect, we know that it is essential to have access to reliable data and tools while following updated methods and guidelines. There are different actually traditional approaches to measure urban heat island, like fixed stations, mobile traverses, remote sensing, and many others, but each of them has its own limitation. For example, remote sensing is really good to measure the horizontal surfaces like roofs, streets, pavements, vegetation, bare grounds, and so on. And it leaves out the temperature of the facade, walls, and also the temperature under the trees.
Parisa, sorry for interrupting you. Are you showing slides?
Yes, I will go in the next, just
okay.
A moment. This is a
because
short.
we only see the title slide. It's okay. I thought it was a technical problem. Sorry.
No problem. And for example, in our project, we are using remote sensing to somehow complete our methodology. And we are trying to apply remote sensing to map land surface temperature, which can help us to have actually several or general overview of quickly finding the critical points of a city, the points that they are exposed to the sun and absorbing lots of energy or solar energy. Then we are zooming in and analyzing that area to actually find out the high-risk area, prioritizing them for taking immediate action, and then to complete our investigation, we visualize the hotspots in 3D to discover the impacts of certain climatic parameters like air temperature and solar radiation on landscape and architectural elements. So in fact, the data and technological tools improve that can provide us the opportunity to improve the previous approaches. And by that, the new models can provide us a platform to analyze the complex and non-deterministic climatic condition to avoid negative impacts of changing climate on buildings and take smarter decisions towards a reduction. So the case study that I would like to share with you is Montreal City. Montreal is also one of the cities that is struggling with extreme weather during both summer and winter periods. In this slide, you can see that we use remote sensing to map land surface temperature. As I told you before, remote sensing, we're starting with remote sensing analyzes that it's somehow orienting us in the first step of actually research to find out where exactly are at high risk. And here we use a hotspot, and you can see that here is a Montreal Island. You can see that Montreal Island is also somehow struggling with hot spots, especially the areas that are industrial areas are located, and also a greenery crowd. There is lack of greenery. And also the downtown of Montreal, which is this part, you can see it here, are also having some hotspots, and we need to take immediate action. So, the project is in the process, and I just choose one actually urban area to show you, which is this area. And in downtown, and we are calling it Place Bonaventure. You can see here the Google Earth map, and we are going to analyze actually this area and somehow to actually use a spatial model to analyze how buildings arrangements, their form, urban material, and so on could contribute to the intensification of urban heat island effect. For that, we use actually 5-dimensional climate plus scenario model that can be performed through a computational platform called Solarc Vision. Solarc Vision developed by Mojtaba Samimi in 2000. I'm working directly with the developer, and we are trying to use the model in different projects. And why we are calling it 5-dimensional model? Because on one hand, this model is based on the 3D model of buildings, shading devices, trees, and topography. And the 4th and 5th dimensions are shaped along climatic and weather data of the location in different hours and seasons. So basically, this model provides us a platform to document the current climate stress in the city and predict improvement potential of future planning opportunity, and at the same time, or last but not least, actually serve as a base for future construction projects or for granting construction permits by placing the new design to the model. And we are slowly trying to expand the model and make it as a one base to somehow give a permission to the new buildings that the people are going to build in their in their cities. And before we start the spatial climatic analysis, we also analyzing the different climatic parameters in the target area, and we should analyze them to understand their impacts in different months and seasons, and then map this climate parameter on the 3D of urban areas and see how urban form and climate somehow interacting with each other. I'm not going through the details of all this analysis because I just wanted to show you to see that what is the process because my main part of the presentation is coming soon. And then we are also analyzing the temperature patterns in order to actually understand which months have a higher temperature and how this impacts on our urban planning and design. And as well as analyzing positive and negative effects of the sun, which is the hottest spot. Hottest spot is not just the areas that are absorbing solar radiation. We have to multiply the patterns of hourly direct radiation and hourly need to shade and shine in order to reach to the hot spots. That later on we are going to actually map this actually analysis on urban area, and you can see that how it's working. And then of course, that we are also analyzing the past climatic condition in order to have a better view of the likely and extreme scenarios in future. Actually, looking to the past, it can actually give us a broad view that how we can design a good future scenarios in order to have a less actually erode in our actually implementation and measures. And after that, we are trying to actually analyze the spatial climatic, spatial climatic analysis in design. And here, actually, a spatial analysis can be applied throughout the whole design process, which will help us to improve the design in regard to the quality of outdoor and indoor spaces. For instance, finding the best position of windows and skylights in regard to improving the energy performance of the building envelopes. As I already mentioned, the undesirable effects or hotspots are calculated by multiplying the hourly amount of direct solar radiation by the degree of need to shade and shine in each hour during different months. That here you can see in the first row, this is the direct solar radiation, and the other one is the need for shade and shine in urban fabric and also building skin, that we can achieve the hotspot that you can see here better in urban fabric. Here actually we mapped these analyses in the existing urban fabric of the case study area, Place Bonaventure, for 19 days from June 1st to September 2nd, because these months were the hottest months in Montreal. And the red spots show high risk area or the most negative performance, and actually blue indicates the most positive climatic actually design performance. This figure actually shows that the roofs and the buildings which oriented to the southeast and southwest, as well as the paths in east-west direction, are considered as the first priorities to take action. And for example, or we also suggested to use the shading devices in some of the buildings facades oriented to the northeast and northwest to improve the climatic performance from yellow to blue. So, actually, after identifying the hotspots and prioritizing them, different scenarios are developed and simulated to find out which of them could have a positive impact on the hotspots. Based on these simulations and by ranking different design choices according to their long-term effect, could be prioritized, and after that we are trying to come up with a mitigation plan to countermeasure the urban heat island area in the target area. And as I said, this project is still in the progress, and I just wanted to share with you one scenario. And here you can see a simulated scenario that by placing trees on one of the hottest area, which is this area, actually we could decrease the temperature dramatically, and in fact trees and actually the trees and vegetation areas can provide desirable shading effects during the summer to improve the climatic performance of that place. Actually, in summer, trees also providing thermal comfort for the citizen and protect them from undesirable solar radiation during the day. And in order to actually to conclude this first part of actually presentation, I would like to mention some key points, like, for example, to optimize the climatic performance of the entire city. Applying the climatic spatial analysis is essential to identify and visualize critical points. And also, a building should not be considered as an individual component. Rather, by placing the building in the target urban area, its impact on the surrounding buildings and vice versa should be examined. For example, one building can show perfect climatic performance alone, but as soon as we are putting this building in the urban area, it's showing completely different climatic performance, and it can impact on the surrounding area or surrounding buildings, and also vice versa. And also, spatial analysis provides a new insight for architects, urban planners, landscape architects, as well as policy and decision makers, and enable them to examine the advantages and disadvantages of a small and major decision in relation to the sun, climate parameters, and future extreme weather condition in each location. And last but not least, we have to keep track of progress and constantly updating and monitoring the model to take a smart decision and achieve urban climate change planning. And in the second part of my presentation, I would like to open a dialogue and discuss further that how this introduced model can somehow bridge the gaps. I mean, of course, we can actually somehow bridge the knowledge gap by empowering the policy and decision makers to take the sustainable decision by bringing these invisible hotspots into their eyes. Since urban heat island is a kind of invisible phenomenon, some decision makers do not prioritize it in their agenda or allocate the budget for that, because they cannot imagine how this phenomena can impact on different aspects of life in long term, and cause tremendous problems, not only on the local level, but also at the regional and global levels. So applying spatial climatic analysis can help us to create somehow a common language to interact with different stakeholders smartly, to bring the problem into their eyes and push them to the direction of resilient urban climate change planning. And it's somehow assure that all the stakeholders perceive the challenge and they are consistent with others in solving problems. And also technological gap, technological tools can also help cities to better identify their challenges, communicate, prepare, and manage any crisis in an uncertain and sophisticated environment. And in this regard, technology acts as a supportive tool to ease and facilitate the process of perceiving challenge in a very complex system, as well as facilitating the process of achieving a mainstream climate action plan. And somehow scenario development gaps. The model can also fill the scenario development gaps by developing different scenarios and simulating them to find out which of them could have a positive impact on the hotspot. Based on this simulation and by ranking different design choices according to their long-term effects could be prioritized. And also the data gap, the model uses open data to map the climate on urban planning and design, which capture insight from various perspectives and motivate innovation by using big data. Simply saying, open data provides new opportunity to tackle the issues. However, accessibility of data is also, open data is also one of the tremendous problems in some actually cities due to the security concerns and data privacy, and they are not willing to share the open data. And however, open data increases transparency in a system and empowers decision makers to decide and act smartly. And this is the discussion. I would like to discuss this further with you in Q&A session. And by that, I would like to also mention that based on the aim of the Innovate for City conference, the introduced approach will enable cities to take accelerated and more ambitious climate action. Thank you so much.
Thank you. Thank you so much, Parisa, for this presentation. Maybe, yeah, great. You can stop screen sharing. So before we start, I would like to know if Maria is here now and if she can speak. I see you. Is your mic working? Have you managed to fix it? Doesn't seem to be. Okay, so then no problem. If you have comments, please write it to the chat, Maria, and we will then, yeah, she can hear us. So then we can read you. That's good. Okay, so thank you, Parisa. You gave us a very nice template for the discussion with the last file that you showed in your presentations that called data, or that called filling the gaps. And I would also like to start with the open data question that you raised. When we set up tools, I know this well, we always try to implement them into well-functioning data ecosystems of cities. So whether we speak about citizen engagement or climate or mobility or housing, it doesn't matter. For us, it's very important to have like transparency portals or open data policies of cities so that a lot of people can use the data and that the data will be accessible for nearly everyone. And this is not always the case, like you said, for security reasons and sometimes also for political reasons in cities. And I would like to hand this over to Pedro immediately, past this question. How is this in your case? When you start working, is it important for you to have open data infrastructures, or how do you combine also your climate data to other city data, like social data, infrastructure data? I mean, a city produces so much data, and climate data are also interesting for other perspectives and disciplines.
So in the case of Buenos Aires, we were very lucky because the city has a very well-structured geospatial data, and we were able to work with very good 3D spatial data to perform our climate modeling system. So we have the height of the buildings, the width of the streets. We can work with very good material, and as you well know, the good you feed your models, the good are the results. So in the case of Buenos Aires, the work was very pleasant. It's very usual, and we have developed similar studies and analysis in several cities in Latin America, Africa, or even in Europe, and it's not as usual as we will expect to have access to very data sources, open data sources. I think you are right. There is a way to move forward. and two, at the first stage, develop this data, and at the second stage, put in available to scientists or to enterprises or to citizens to use this data. But it's an open field of work, in fact, to move forward.
I wanted to say also the audience can ask questions, of course. Now you can just maybe turn on your camera and raise your hand. We are not so many people, so then I can see you and you can start speaking. Again, since we are talking here in the context of UN Habitat, and I know that we do work a lot in cities that don't have such a good data infrastructure, sometimes the quality of the data is also not so good. How do you work there? How would you, for example, Parisa, go to cities? I know that you work also in the Global South, but how do you approach this if you realize that there is not data, or there's only a certain kind of data? What we also very often have a disbalance between having a lot of mobility and infrastructure data, but don't have social data, for example. This is something that I observe very often.
Yes, actually, especially, for example, I work in Cairo. There are lots of unplanned areas there. So basically, finding the data in these areas is really difficult because there's no data, because they're building the buildings and they're not mapped already, and you cannot really refer to that data. So actually, this is my slogan, and I'm saying all the time that we have to start from a point, and we cannot all the time see it and say that, okay, we don't have a data, so we cannot do anything. But we have to start from one point and collect the data with different approaches. For example, in unplanned area where there's no data exists, we try to use the different approaches. We used remote sensing and also site analysis. We try to use a survey, and as well as actually, and at that time, use ENVIMET for simulating these areas. And we had a group of students. They could actually also make a 3D for that area for us. So we could start from one point and push it forward. And then when you have some result in your hand, you can show it to the decision makers and push them in the direction to put a budget, allocate a budget for this kind of stuff. And we can have actually try to actually collect more data and make it available for not only for the researchers, but also for the other people. And the other thing is, actually just having the data is not actually case, because just having the data is not actually visualizing the challenge for decision makers. We have to also have a good tools, as we already mentioned, to simulate them, to transform them from data to something that we can see, connect, and see where is the challenge. I work already with some cities that they didn't even know. I mean, decision makers didn't know what is climate change. So you have to really build up common language and start even with the really small steps to move towards this direction.
Mm-hmm. Thank you. I see Naomi raising her hand. Is that right?
Hi, yes, it's Naomi. Thank you all so much for such a wonderful presentation. For me, this was very enlightening to hear and think about. And I'm curious, you all were talking a lot about the data that you're working on and just how you're able to see the impact of these areas as they work together. But as someone who's working more on the city side of things and really thinking about implementation, right? I know we still have lots of data that's not there, but are you guys integrating, or how are you working with like city governments or committees in the city governments to actually get them to begin implementing policies based on this great data that you've collected? Thank you.
Thank you, Naomi. In my case, my clients are city governments, and we are aiming to give them the tools to make the best decisions. So if these decisions are science-supported decisions, we probably are moving on the right side, on the right direction. in fact, we sometimes know how to make good interventions in our city, but we don't know exactly which is the impact, or we have to how to manage in terms of cost benefit our measures. So it is a very important point, and sometimes you think that, for example, you put a lot of trees in a place, but if you don't bear in mind that the wind direction and the wind flows are interrupted by these trees, maybe you have an not expected effect in terms on air quality. So you have to know these kind of things, and you have to bear in mind these kind of things to make the right decision. So we provide this science, practical science to city level, the make a decision departments, and that we have to work with.
Yes, I can also add something. Actually, as Pedro said, this is definitely like this. We are working directly with the government or the implementers or practitioners, let's say, as well, and trying to find out how we can first of all connect with them or interact with them to show where is the challenge. And we're trying also to suggest some scenarios, and we are trying to analyze and simulate actually in these scenarios and prioritizing them and offering to them and telling them, writing an action plan and giving to them. We can and also we offer to implement a pilot project and trying it. And if actually after several months or a year, this actually measure could work in that scale, we are trying to actually expand it for whole city.
Is this an answer to your question, Naomi?
Yes, no, it's very helpful. I'm just curious about it. So I'm currently a grad student, and I'm actually leading the federal government here in the US. And so I oftentimes see folks who've done a lot of really intense research like you all have done to try and provide the science, but there's a gap, particularly at the local level. And so just curious in your context is like you're talking about how you're able to start having those conversations. And then also was really curious because I know if you guys have looked at the website for Innovate for Cities, they kind of have these step-by-step metrics of how cities are supposed to be moving. So curious where this fit into the process of helping cities develop plans and implement policies. And so, yeah, thank you all so much.
Yeah.
Yeah, I think your question is very important, and I would also like to add something. I did not present, but in my case, I'm based in Hamburg. There is a lab, it calls the City Science Lab, that is really seed funded by the city, and we also invent such tools, and we are part of the digital strategy of the city of Hamburg. And this is our connection to the city. So every tool that we are going to invite is implemented in the city. We are not allowed in a way to do like something that won't run then afterwards in the city. So this can be also a strategy to include research labs into the digital strategy of a city, and then you are officially part of it. And then we can also connect to companies like Pedro's company or Parisa's company, and then they really work with the authorities of the cities. Because I think really what you say, it's right, there's very often a gap between a lot of people that are very innovative, but the city council, they don't even realize that there are those people in the city. That's
our efforts feed urban planning processes and climate action planning for cities. So it moves on and it's put on the terrain and goes transforming in a practical way. So we are not theorizing. That's the way that we have to work in terms of in a practical way.
Yeah, and Maria, she just put in the chat, science data must be always available to the governments. Also the other way around, the government data must be available for science. This is this open data policy that we are always looking for. Yeah, thank you. I have another question to you, this is also for Maria. The Mendoza example and Pedro, yours examples, they were really hyper-local. You speak about a square meter, Pedro, and Maria spoke about, I think, 250 and 250 meters. So it's very small scale, but it's good because it's very concrete and very detailed. How can you transfer this to other regions or make it bigger, scale it up? Because the typologies that you choose were also very, very specific, of course. How is it when you go to another city? How do you implement other typologies, or can you transfer the typologies also to other areas?
We work in a mesoscale scale with a resolution of 1 square kilometer, and we in this case we used the definition of local climate zones. It's an international, well-known methodology that it was in fact implemented in many cities around the world, and it is it allows comparison between cities, and it's a well-developed and well-known methodology to implement and to model close to real urban parametrizations in terms of urban climate. So our contribution is applicable to all kinds of cities around the world, because we have to work with these pre-designed local climate zones. You can manage in the mesoscale meteorological model some kind of parameters, specific parameters, but they work in every kind of city in the world. In the bibliography that we mentioned in our presentation, you can find, I will share the references in the chat, but you can find there are these local climate zones that apply in every city of the world. So it's a methodology that we can work iterative in a iterative way.
Yeah, so it's an established scale or size and methodology. Yeah.
Yeah.
Okay. Yeah. And also Maria, she put something in the chat. In our case, we try to parametrize our space. In Latin America cities, we had a similar urbanistic design. Spanish inheritance. The challenge is to adapt to a specific climate. Yeah. Okay. Yeah. There is a question from Andreas Rubin. I think you have to unmute.
Yes, just would. I have a question about the costs, because I'm also working in this field, the university, the ETH of Zurich, and cost is always one of these critical questions, because most villages or even cities say the costs are too high for this analysis. So how do you actually get into this, doing this analysis? Where do you get commissions?
Thank you, Andreas. In fact, right now, in terms of practical experiences, we have a wide database of cost of implementation of these kind of mitigation measures, and specifically speaking about urban heat effect, cool roofs and cool pavements maybe are the best cost-benefit options. If you speak more widely regarding other effects, you can choose trees, arborization, parks, but if you reduce the albedo in your city, cool roofs are the best option that we can work for. And in some kind of cities that they have not much resources, we are recommending, we are suggesting, and we have previously success experiences working with these paints, with cool materials that are highly effective in this specific terms of heat urban effect.
Yeah, this was not really the question. The question is more like actually doing the analysis. They even say for doing the analysis, it's too costly. For example,
yeah.
if we're doing what you did for Buenos Aires, I don't know how much it costed, but it's quite a budget.
It's hard to say how much it costs because it depends on the baseline data you have to work with, and in this case we only could work with 10 days period in the summertime, in the winter time, and we have to move faster. It was a 3-month assignment with 4 people working and a supercomputer working as well. So you can make your own your own figures, but it took for us 4 months at least. But we run only 2 periods of 10 days. So computation, it's a very important cost to take into account in this kind of process, because the random model, the WRF model, the mesoscale model is not easy, and you have to invest much effort to run it properly.
And just one thing I add, actually, of course, it will be costly if we don't have that much data, because we have to spend lots of time also to pre-produce the data as well as preparation, and this is gonna increase the cost. But actually, if you have a good data and have access to open data, is not gonna be a big deal, and with a less budget, not really less budget, but affordable budget, you can analyze this. It depends on the, of course, on the scales of simulation, which scale you're gonna choose, just one urban area, or as I said, you're going to expand it for a whole city center, and try to also use this model as a actually base to give a permission to the building for the construction and so on. So all of them depends on how and in which scale you're going to actually simulate. So all of them can somehow impact on the cost. But as I said, we can start with the really small steps and slowly pushing it forward. We can start with, I don't know, let's say 10,000 euro, and then slowly putting a budget and moving it forward. I think is not something impossible.
And I connect to your question, Andreas. One cost factor is setting up such a tool, and the other cost factor then is maintaining it. How do you ensure that this tools will be maintained like they have? You have to feed it constantly with data. There are people that have to use it and update it from time to time. How is this working?
Well, we're not really maintaining a tool. We just did analysis of parts of a city, and then deduct from that the possible solutions.
You are from a university, more like?
Yeah, we did a study together with the city of Zurich for one region of the city.
Yeah, ETH, you said.
Certain influence of cold air streams, and then analyzing different building geometries and different tree types in a street, how it affects the wind flow, the cold wind flow during the night, and what the effect it has on temperature.
Mm-hmm. And how is it in your case, Pedro or Parisa, the maintaining issue?
I can answer this. As soon as government get the ownership of this actually model, they can put, hire 2-3 people that they are constantly actually updating or monitoring the model. It's not a problem.
But this is coming back to Naomi's question from the beginning, and it's very important for us when we set up such tools. We have a local state agency in Hamburg, for example. A lot of cities have that. They host the data, they take care of the quality of data, they maintain all data innovations that take place in the city, and that's very important then for us, because we hand it over then to this agency, and then they feed it constantly with data. This is also very important for us, and this is also very different in cities.
I mean, for us, well, one question is now more actually in cities, the quality of the surface, to know the quality of the surface, so the surface properties. And not only because we are actually some modeling, well, not myself, but colleagues, modeling at 30 centimeters grid cell, smallest ones. So really local. And so we really need to know what the surface property is and the moisture content and all this.
Yeah, and do you have data protection challenges in Zurich when you do it?
There's open data. Yeah, it's most things are open data. So building size and all these building geometries are available. So that's quite good.
Yeah. Are you raising your hand? Yes, huh? Mm-hmm.
Yes. So I had a question kind of building off what you all are talking about and thinking about, particularly with the data collection and the need for it to somewhat be hyper local. I know we've been talking a lot about kind of the companies and the universities doing data collection, but wondering, I don't know how complex the process is, but is it possible to have some sort of local data collection? And what I'm thinking of is something like OpenStreetMaps, or things like when there's hurricanes in Haiti, right? They oftentimes rely on local actors to actually provide information that's then uploaded to a larger data system, so that you get data points in places where if it's just kind of like a group of highly trained individuals, such as yourselves, you can't do enough of it. But if you're able in some ways to have the local community do some of the data collection, then you have consistent information, and then also, you know, the ability to do it over longer stretches of time.
Yeah, you're right. This kind of data can be updated and modified by citizens. But I think that the main investment effort is the first stage. You have to complete a city-sized 3D model, and then it's not that difficult to maintain this structure, and you don't have to keep it up to date minute after minute, because it's not as much as necessary for our kind of studies. But you have you may update this data periodically, even 5 years, even 10 years. So the cities changes, but not as fast as to follow it minute after minute. So I think that the city has to make this first financial effort, but I think that the return that the city gains with this effort, it's multiple, and helps the city makers, the bodies make best decisions.
Yeah, I'm just curious about it because I'm thinking about things such as OpenStreetMap and another program that I'm not going to butcher the name of, where they kind of take a flat, which isn't 3D, but they have a base model, and then a lot of that work is oftentimes done by sometimes trained individuals, depending on how complex it is, and then other times just, you know, interested citizens. So curious, you know, how much of it really, I know we in a model where we're used to the city kind of having to be the primary actor, but is there ability to kind of use other folks to fill gaps that we just don't have the financial capacity or the number of staffing, right, to do through traditional means?
Can I say something? It's in Germany, we have a lot of activists that are very active in this area. So sensors are getting cheaper and cheaper. So they put the sensors on their backpack, then they drive through the city center, and they collect data and set up alternative mappings, for example, for the city of Hamburg. And we try to integrate those citizen data more and more also to the master portal. It's still not sufficient from my point of view, but they are trying to do it more and more. But the problem or the challenge in this issue is, from my point of view, but maybe this is different in other cities, climate data and also air quality data are highly regulated. If a city, they have like air quality plans that they have to fulfill every year. And they have very certified sensors that they are collecting those data for air quality, for example. And when the citizens come there with their data that are different, they measure different components of air quality, for example, then you cannot use it for this official plan that the city has to apply or has to fulfill every year. So this is a political argument at the moment between the activists and the official politics who are forced to collect those data. I don't know how this is in Madrid or also in Montreal or other cities, but in Germany it's an issue because the activists there are getting stronger and stronger.
I think that machine learning practices will fill this gap in the next future. But you are right. Here in Madrid, you have to fulfill the European legal framework, and but we are working here with mobile devices to measure air quality or urban climate. But you have we only are not able to connect with the official air quality network and air quality parameters, legal parameters to measure our real air quality. So, but in the next few years, we are going to solve it for sure. I'm pretty sure about that.
I have another question, and then time is nearly up. My last question: do you think that there is, after the pandemic now, have you observed changes, or are there other needs of measuring in different ways? Because do you think there is a difference now, before and after?
That's a tricky question, because all the environmental problems remain before and after the pandemic, and we have to act strongly against these climate concerns and these environmental concerns, and the way we have to act, in my case, remains and is still intact. So maybe the pandemic changed a lot of things in our lives, but in my particular case, it has make strong my commitment with this kind of problems in the city. So we have to keep working on it and move forward faster.
Actually, it's also, we have to see it from which perspective we want to see that. For example, climate change somehow increasing or intensifying the impacts of pandemic as well. Because when we don't have, let's say, air quality, or when the cities are suffering from heat island, of course, it's going to be lots of pressure on the citizens, and on top, pandemic is coming and making lots of problems. But still, I think we are still in that process, and we have to push it as much as possible, because we also have a pandemic as well. So we have to move somehow tackling climate change and COVID together, or pandemic together, to have better cities, because it's not just a matter of the cities, also just a matter of the citizens. Somehow we have to take care of both at the same time.
Yeah, and regarding the urban island effect, we have to promote nature-based solutions, green infrastructure in urban environments. We have to promote well-designed urban regeneration and well-planned new urban developments. So I think that these are the ways we have to move to deal with this urban island effect.
Yeah. Okay, so the time is nearly up. I thank you so much, Pedro, Parisa, and also Maria, for your great presentations and insights, and also for the discussion. Maria put her contact to the chat, so if you want to get in touch with her, you can find her at ResearchGate. And thank you also to the audience for the discussion. And I wanted to say at the end that the whole panel here, it was also to update the global research and action agenda on cities and climate change. So we will summarize your inputs, your insights, also to update this this text, and at the end, this policy that the UN is going to write for all the cities in the world. So I thank you so much for being here with us, and I wish you a happy whatever morning, afternoon, wherever you stay. Hope to see you soon.
Thank you so
Thank you.
much. Bye-bye.
Thank you, everybody. Bye-bye.
Thank you so much. Good job.
Oh,